Hey guys, so to finish off what we didn't quite get to in class, I did put instructions in Schoology, but not just with these locus definitions, please also draw a diagram, and the book is including diagrams, of what the locus definition is talking about, so you have that as reference. So there's the one for the ellipse, and then when you flip over, and the hyperbola and parabola also have directly a graph reference for it, so you can make sure you're clear on exactly what distances we're talking about here, because these can tend to get a little bit confusing with the wording, so just getting used to what it's saying. And then the last big thing I want you guys to have is an actual physical tangible example with numbers to go with each one. Now luckily I'm going to provide them for you here and select a few that go with the problem set here. Remember, this time I'm not assigning the problem set for 6.6, but I'll select a few from this problem set that go with each one. So if we start out with the problem set number 2, and you can look in the book right now yourselves. I'm not gonna actually hover my camera over the book. But basically the things to know here are our focus 1 is negative 3, 0. Oh, actually it's positive 3, 0. And focus 2 is negative 3, 0. And then the string length given to us in this one is 10. So what we're saying is the set of all points, right? And so our point in general, we'll call it P, we just call xy. But what we're saying is the sum of the distances from xy to f1 plus the distance from xy to f2 equals s, right? So really f1p plus f2p equals s. So all we really need to do is write an expression here that represents this distance, and we already know s is 10, so we'll just put 10 there. The good thing is, again, distance formula kind of to the rescue here. So we'll kind of set this up just like this. Distance formula plus other distance formula equals 10. And remember, it's just simply the difference in x's squared plus the difference in y's squared underneath. So in this case, x minus 3 squared plus, and luckily that's 0, so this is just going to be y squared. And then this one's going to be plus 3, x plus 3 squared, and then plus y squared. And so guess what? Here is a point tester equation. Now there's actually different questions question 2 asks in the problem set, and I'm not really a fan of how they set it up, which is part of the reason why I'm kind of skipping the problem set here. But if you want to set up a point tester equation based on that locus definition, you essentially can just think about what an ellipse means, and then just use the distance formula for those two pieces, and then whatever the string length is, just put it there. Now this is what we kind of ended talking about in the class period today that I sort of very much skimmed through. This is what I actually started out with. So if you wanted to actually finish this out, you could just leave this as is. It is a point tester equation and it's valid. But there actually turns out to be simpler ways to write equations for these than leaving them with square roots. So if we actually took that equation, I accidentally wrote it twice here, so this first and second step are identical. But if you took the equation we just wrote there, and you worked with it, kind of like when we did in 6.1 problem set in the last video that I showed you, we're going to have to square things to get rid of the square roots. But since there's 2 square roots, we're going to have to square twice. And it creates this big mess. It's a big algebraic mess that you have to slog through. But the cool thing is, once you slog through all that, and I made a few mistakes along the way, which obviously shows us that it's a pain, right? It's easy to make mistakes in these things. But I finally got it all correct and simplified this. And what I did was just simplify everything, no more roots, and put all the x's and y's on one side of the equation. And in the end, I actually got something that looks much, much nicer than what I started with. I got this right here. But it is standard to make the right side equal 1, which we'll talk about later at a different lesson. And here turns out to be the really nice form of the equation for that ellipse. Notice that this plus sign is still preserved here. That still actually relates to that initial plus sign of the sum of the distances. So you can appreciate this work. You don't need to write all this work down, but what you should do is write up the setup here. Okay, write the setup here, and then what you can do is just skip to the very end, and you can actually write that this is the final simplified version of the equation. I don't need you to actually write all the steps in between. Another example, so that was the ellipse. An example of a hyperbola is given in question 4 on this problem set. And in a similar fashion, we can set up question 4 like we did before, and we can use F1 and F2 again. In the definition here, I don't know why they stopped using F1 and F2 and they use A and B. Really, it doesn't matter if we use A and B or F1, F2, but just remember that the A and B are still the foci of this hyperbola, right? So I'll just stick with this and use A and B. In question 4, it gives us actually the same foci, actually, 3, 0, and negative 3, 0. But since the definition is different in a hyperbola, right, it's the difference in the distances, not the sum, we're going to have a really similar setup actually here. And technically it's the absolute value of the distances, because that basically is what creates the two things there, because you could switch this difference around and still get the same thing. So really our setup's the same. We have the x minus 3 squared and then plus y squared. And then, whoops, I even just made a mistake. I almost wrote the sum there. This is the difference now. So minus the square root of, again, same exact setup because the foci are the same. That distance is equal to, and I think even we're saying that difference in distances is 10 again. Oh, nope, I was wrong. Made another mistake. My bad. And again, remember, you don't need to do all the long work that I'm going to show you in a minute. The distance in this case is 4, actually. But they did give us the difference in distances still, I guess, as the same concept here. So you'll notice the algebra work is really going to be the same thing. We're going to have to go through and square twice. Now, technically speaking, this is absolute value. But since we're going to end up squaring to simplify this, that absolute value is not really going to matter, actually, at that point. And I took the liberty of doing this work ahead of time as well. And what I did first is, I actually skipped a step here, is this is minus and I added that to the other side. So then I got this root equals this plus 4. And then I squared things, and I did all this algebra work, and this one worked out to be, although I didn't actually write the final other form like we talked about before, this works out to be this right here. And if you actually were to do this, it would be better stated as 1.25 is 5 over 4. So actually, this could rearrange to be 5 over 4 x squared minus y squared equals positive 5. And don't worry about feeling like you have to follow through this. I'm just kind of sharing with you. And this ends up being x squared over 4 minus y squared over 5 equals 1. And yet again, we have a format that looks suspiciously similar to the final format we got with the ellipse thing right here. And so the only difference, of course, is that instead of this being a sum, it's now a difference. So again, it still preserves that sum and difference portion of the definition from the locus, even though we started with this really ugly square root business, because that's the most direct way of using that definition, and we ended up with something that looks a whole lot nicer actually than that. And again, we're going to get to looking at what this format is saying and what it means to us in the next lesson, which is way easier to work with than the square roots. Okay, so there's the definition, or there's the example you can use to put in your notes for hyperbolas. And parabolas, luckily for us, we've actually already done some work with parabolas, but so you could use an example from a previous thing. But question 6 is a good one. In fact, actually, really it's question 9. I'm going to flip to that. Yeah, really it's question 9 that directly asks you to find an equation. 6, 7, and 8 are all kind of revolving around the same example. But question 9 says, equation of the parabola with focus at 1, 0, and the directrix with equation x equals negative 1. Now, in class, I didn't directly mention what the directrix is. The directrix is the fixed line that the definition is based off of a parabola. So what we're saying is here at negative 1 we have this, we have that line, and that's that directrix. Okay, that's that fixed line the parabola is defined after. And then it says focus at 1, 0. So if I put the focus here at 1, 0. And we've already learned that the parabola itself is kind of stuck between these. In fact, right here it has to be equidistant, so we know the vertex is halfway between here. And at some point, this isn't going to be perfect, but the parabola kind of does something like that. But this is the collection of all points, remember, whose distance is from these points, okay? So P, that's distance to this focus is equal from it as its distance is to that line x equals -1. And the good thing is, this is another one where we can just set it up. And if we set this up, we're going to get, well, the distance from this point to this point, and remember P we can label as x, y with its coordinates, can just be another distance formula. So if I want to go to the point 1, 0, because that's the focus here, then we have x minus 1 squared plus, and again since the y coordinate is 0, that just stays y squared. And that distance equals, the good thing about this, it's a horizontal distance always, so we don't need to use a distance formula here. Remember that we just use the absolute value of x minus 1 actually, just like we did when we learned this before. And then we can just deal with this like we did before. Okay, how do I undo this 1 square root? We square both sides, and we square both sides of that, and we get x minus 1 squared plus y squared equals, what do I get when I square this? It's going to be, well actually, you know what? It looks like what I get here is x minus 1 squared, and the absolute value doesn't really matter because when you square it, that kind of makes it irrelevant. Look what I have on the right side, x minus 1 squared. Seems like that is, oh actually, never mind, I made a mistake guys. This should be a plus 1. They shouldn't cancel out. So now we're going to be left with x squared minus 2x plus 1 plus y squared equals x squared plus 2x plus 1. And we can see how a bunch of this stuff cancels out, and the plus 1's cancel out, and what we're left with here is y squared equals 4x, it looks like. Y squared equals 4x. And if we wanted, we could say x equals 1/4 y squared. And you can see that this is a parabola, although instead of x being squared, the y is squared. And that's why this is a sideways parabola and not like a vertical parabola. So there's the general gist of everything, and those are the examples you can use to add in to finish off your notes for this lesson. And we'll talk to you guys later.